This video is on topic 17, simplifying radical. We will be simplifying radicals using two techniques, the idea of prime factorization to help us, or looking for the product of perfect squares. We're also going to talk about how we deal with the square roots of negative numbers. That'll be with the use of the imaginary unit, which is the square root of -1. So, starting off, a review of taking the square root of things. When we talk about just roots in general, when we say the nth root, the index of the root is the little number that's in the upper corner of the root that tells us what type of root we are taking. It sits on the radical symbol that's listed there. By default, if I have a root and there is no number listed there, it is defaulted to be the square root. The default is to the square root of 2, or just we call it the root of 2. Things underneath the root, the radical symbol, are called the radicand or the argument. We will talk about how this root, any exponents on the radical argument and the index are related in future units, but there is a relationship listed in there. But again, here we're focusing mostly on square roots. We've already been introduced to the idea of taking square roots, something called perfect squares before. If I ask you to fill out and take the square root of these perfect squares, you should be able to do it all the way from 1 all the way up to 15. For instance, if the square root of 16 we should know is 4. The square root of 144 is 12. The square root of 64 is 8. These are values that we should be familiar with. Now, I would like to make note that the positive square root of a number is called the principal square root. Notice on each of these, we can default to say that these are in fact asking for the principal square root. So notice my answer here is a +1, +2, +3, etc. We will talk about when we add a plus or minus in on a future lesson. But right now, in terms of, we're looking for the positive principal square root. Now, with these perfect squares in mind, how do we deal with numbers that aren't perfect squares? So we come to the idea of simplifying square roots using two methods. One is by using the idea of prime factorization or factor trees, and the other is the idea of working or looking for a product, meaning multiplication, of these perfect square values that are listed above. Now, I don't actually care which method you choose to use moving forward. I'm going to show and illustrate both. It's up to you which method you prefer to use. So, starting with the prime factorization factor tree, which maybe we're more familiar with, if I'm asking you to find the square root of 72, 72 is not a perfect square. However, we could rewrite this in terms of its factor tree. So coming over here, 72, if I'm doing a factor tree, we could do 8 and 9, which is 2 and 4, which is 2 and 2. And 9, of course, is 3 and 3. So, rewriting 72 as 2 times 2 times 2 times 3 times 3. So I'm going to rewrite the number underneath the radical as its prime factorization. Now, as an aside for you, if we're not very good at doing factor trees, on your list of prime factorization and factor pairs that we have been utilizing, I will remind you that the first line in each of these numbers, so if I come to 72, not only have we listed all the numbers that multiply together to be 72, but the first line in each of these lists the prime factorization for all of the numbers. A side note, when it says prime underneath 71, that means that we are just, the only numbers that multiply together are 1 times 71. That would be prime, meaning that this is in fact the prime factorization as well. Same thing over here with 79. Prime means that, hey, this first line, the only numbers that multiply together is in fact the prime factorization. So as we're moving forward, feel free to use this sheet as a reference guide for all the numbers up to 110 in terms of their prime factorizations as well. Now, going back to this for prime factorization. Again, we are defaulting here to doing the square root, meaning that we are looking for pairs of numbers. So if I asked you to pair up the numbers underneath the square root, you would probably say, well, there is a pair of 2's. We have one pair of 2's. And we also have a pair of 3's. Well, anything we pull outside of the radical, we are going to default to use multiplication on. And now if I asked you, well, what things are left still underneath this radical? Well, you would say, well, hey, that 2 didn't get a pair, so it is still stuck underneath. So, simplifying this down now, 2 times 3 gives me a value of 6, and we have the 2 underneath the radical which is the square root of 2. This is the simplified version of the square root of 72. It is written with the smallest number possible underneath, the smallest, simplest number underneath the radical, and values, coefficients on the outside. Okay, factor tree approach, very, very simple, looking for pairs of numbers, multiplying things on the outside. Now, a more direct method is using a product of perfect squares idea, meaning that we are looking for things, we're looking for numbers that multiply with a perfect square, the biggest perfect square possible. So, thinking about it, or let's go back over to our prime factorization, our pairs of values. Here is 72. Looking at this list of all the numbers that multiply together to give us 72, you should recognize that there is 4 is a perfect square, and 36 is a perfect square that shows up as a factor of 72, as a factor pair of that multiply to 72. Well, if I'm looking for the biggest value, the biggest perfect square that is multiplied in with 72, we would be looking at this level. So I'm going to go back over here and rewrite 72 as the square root of 36 times 2. Now, why would this be helpful? Well, do we know what the square root of 36 is? Well, yeah, we know that the square root of 36 is just a 6. Well, we can't just get rid of that 2, right? So we would just leave that 2 underneath the radical, and we would again come up with the answer of the square root of 6 times the square root of 2. Notice, in both of these instances, I get the same exact answer, whether I'm using prime factorization or I'm using the product of perfect squares. Pros and cons of each. Prime factorization, we've done a lot of work with prime factorization or factor trees in this class and in your previous lessons, so kind of just knowing how to do those is a little bit easier, especially if you have bigger numbers that don't fall on the sheet. Product of perfect squares, though, if we get a number that falls on less than 110, we kind of can look and see what the perfect square values are. It's a lot quicker, less math for us to do. However you choose to proceed is up to you. Let's take a look at these 3 examples. Why don't you go ahead and give those a try, and I'll show you the answer here in 3, 2, 1. Here are our answers using both methods. Square root of 32 ends up being 4 root 2 using prime factorization or product of perfect squares. 96 square root ends up being 4 root 6 using both methods. And square root of 156, this number is off the sheet, so we have to do a little bit more work, but we get 2 square root of 39 as my answer. Now, up to this point, we have been using and taking square roots your entire life of just positive numbers. Well, how do we deal with taking the square roots of negative numbers? Up to this point, I haven't been able to do it. Right? We just said this is impossible, cannot exist, no solution. Well, we actually have a workaround that we're going to use, and that is involved using this idea of an imaginary number, okay, a number that doesn't actually exist. We are going to define the imaginary unit. We're going to use the letter I for imaginary unit, and we're going to use this number, I, to represent when I have a square root of a negative 1. Okay? So as a workaround, if I have a square root of some negative values, let's say negative a, if I think about it as the square root of negative 1 times the square root of a, we could say, oh, the square root of negative 1, we're going to pull that out and write it as the letter I, and then proceed as we normally would with just the square root of whatever number a is. Okay, so it's kind of a workaround to say, all right, well, I know how to solve it if it was a positive number. Well, let's pull that negative out, write it as the letter I, and then go about our normal business. So let's take a look at the square root of 50. We have a negative number. So what we're going to do is we're going to write this as the square root of negative 1 times 50 underneath the square root, or the square root of negative 1 times the square root of 50. Well, we know that the square root of negative 1 is just representative of we're going to use it as the number I. Now, all we are going to do is we're going to proceed by simplifying the square root of 50, just like we did up above, either using prime factorization or product of perfect square idea, and multiply our answer just with an I along with whatever numbers we happen to pull out. So simplifying the square root of 50 either with prime factorization or product of perfect squares, we get an answer of 5 root 2. Well, that means then we would just have I times 5 times the square root of 2. Now, it is generally good form in math to write the letter second, so we are going to write our final answer as 5I square root of 2. The variable looks weird listed in front, right? Just think about it. When we write 2x, we don't write x2. It just looks odd. So here is, in fact, our final answer for when I simplify the square root of negative 50. Again, pulling out the square root of negative 1, writing it as I, and then proceeding as normal. Let's take a look at the square root of negative 81. Well, to start, I can't take the square root of a negative number, so I'm going to think about it as the square root of negative 1, which we're going to write as I, and then simply multiply that by whatever the square root of 81 is going to be. So, using either method, well, in this case, we don't really need to use the method because the square root of 81 is a perfect square, and this is just going to be 9. So this would turn into I times 9, which we will write as just 9I for my final answer. Okay? Why don't you go ahead and give the last 3 a try? I'll reveal the answer in 3, 2, 1. Here are our answers. Square root of negative 54 turns into 3I root 6. Square root of negative 33 turns into I root 33. Now notice here, this is our first real example where 33, it's just a prime number. There are no factor pairs. There is no perfect square that goes there, so we can't simplify it any farther. So the only thing we were able to do is pull out that negative 1 as an I, giving us I root 33. And lastly, negative square root of 180, we get 6I root 5. This should be enough for us to help us do the review, simplifying roots with negative values and simplifying square roots of positive values. Same combination, just remembering the square root of negative 1 is this imaginary unit of I.